We're now going to have a look at how we can calculate the standard enthalpy change of combustion by doing an experiment. So firstly, I'm going to run through what the definition is again, and then how we set up the experiment. Then I'm going to work through a question where we are calculating the standard enthalpy change of combustion, and then lastly, we're going to look at how accurate that experiment is. So first things first, let's have a look at the definition again. So the standard enthalpy change of combustion is the enthalpy change that takes place when 1 mole of a substance, so that's the important part here, reacts completely with oxygen, with everything being under standard conditions and all reactants and products being in their standard states as usual. Okay, so in the example that I'm going to go through today, the fuel that we're going to be talking about is methanol. So let's now write out the enthalpy change of combustion equation for methanol. So the formula for methanol is CH3OH. Don't worry too much at the moment if you didn't know that. And it's a liquid fuel, so it's going to be the liquid state symbol. If we are doing the combustion reaction, as always, we will then react it with oxygen gas. And because it's complete combustion with oxygen, we are going to form carbon dioxide gas, and we are going to form water in the liquid state because it's got to be in its standard state. And then to match the definition, we've got to make sure we only have 1 mole of the methanol being burnt. So in order to balance this, we need to have 2 waters, and we therefore need to have 3/2 oxygens present. Okay, let's now have a look at the setup of the experiment. So we will hopefully get a chance to do this experiment in the classroom, but for now we're just going to have to run through how it's set up on the screen. So over here at the bottom we have our spirit burner. Now this spirit burner usually has this wick in it, and our liquid fuel is going to be found in here. So let's imagine that we have our methanol in this spirit burner over here. And then at the top over here it says copper can. It can be anything, so we could have used a beaker, anything that's obviously not flammable. So we've got this copper can over here. In this copper can we put our water, and you need to know what the volume of the water is because that's important when it comes to our calculation. Okay, so we are burning our fuel down here, and the water is essentially acting as the surroundings. Okay, so we want to see how much energy is being transferred from this chemical system here to the water here, so going from our chemical system to the surroundings. And within that surrounding we are putting our thermometer, and that's going to give us our reading. Okay, so when we do this experiment, we have to write, before we even start burning anything, we have to write down a few values before we can get started. Okay, so the first thing that you need to do is make sure you know what the volume of water is. Okay, so I mean it depends on how you want to do it, but usually the experiment method will tell you how much water to add. We also then need to take the initial temperature of the water. Okay, so before we start burning anything, you have to write down the volume of the water and the initial temperature of the water. Okay, so we can actually keep the thermometer in there. Once we start burning, we can keep stirring it with that thermometer. We also, before starting the experiment, we do also need to take down the mass of our spirit burner. Okay, so 3 measurements we need to take down: volume of water, temperature of water, and the mass of the spirit burner. Okay, and then we can start our experiment. So we light our spirit burner, and what we do is we let that burn for a little while, usually about 3 to 5 minutes. The time here isn't important. Okay, so that's not a variable that we're measuring. It just needs to be for a considerable amount of time for our water to heat up slightly. Okay, once we've decided to end the experiment, we extinguish the flame. And then very, very quickly, so as I said, you should be stirring your water during the experiment. What you need to do very quickly is write down the final temperature of the water. Okay, so we've got our initial temperature, we've got a final temperature, and then also we should reweigh our spirit burner. We want to basically see how much fuel has been burnt during that process. Okay. And then once we've done that, we are going to, I'm just going to move to a results table. So we're going to run through what to do with all these values once we've done our experiment, how from this we're going to calculate the enthalpy change of combustion. Okay. So as I said, we've got the mass of the spirit burner before burning and the mass of the spirit burner after burning. And taking away the mass before burning, so taking the mass of the spirit burner after burning away from the mass of the spirit burner before burning, we can essentially get the mass of the fuel burn. Okay, so that's going to be important at one point. As I said, the volume of water is also important. So we've got that. We've got our initial temperature of water and our final temperature of water. And from that, if we do the final temperature take away the initial temperature, we can get our temperature change. So this essentially in our equation is going to be our delta T. Okay, so our change in temperature. So if you remember the equation to work out the energy change, so we're going to work out the energy change first. That is Q equals mc delta T. Okay, so firstly we need to decide what m is, what c is, and what delta T is. Delta T we've already calculated by doing the final temperature minus the initial temperature, so that is 41. Just bear in mind, I'm just going to mention this again, the temperature here has been measured in degrees Celsius. You don't here need to convert to Kelvin because we're working out the difference. The difference is going to be the same whether these values are in Kelvin or in degrees Celsius. Okay, so don't worry at this point of converting anything to Kelvin. We can just keep it in degrees Celsius because we're working out the difference. So that stays as 41 degrees Celsius. And over here, the specific heat capacity, which is our value C, we've been told that for water, the specific heat capacity is 4.18. And the mass, now this is very important because we've actually got two things we can possibly have the mass for. Okay, we worked out the mass of fuel burnt. The volume of water is 150 centimeters cubed. We've been told that the density is 1 gram per centimeter cube. So that tells us that this volume, because essentially what that means is that 1 centimeter cubed equals 1 gram. So this over here equals 150 grams of water. Okay, so we've got two masses here. Now it's very important to use the correct mass here. As we said, this m in Q equals mc delta T is the mass of the surroundings. Okay, and earlier I said that the water is part of the surroundings here. We want to see how much energy is transferred from the system to the water, which is our surroundings. So it's very important here that we use the mass of the surroundings, which in this case is the water. So here it's 150 grams. Okay, if you use the mass of the fuel burnt, that's irrelevant here and you'll get the wrong answer. Okay, right, if I now plug all those values into my Q, so that's going to be mass of water, which is 150, multiplied by specific heat capacity, 4.18, multiplied by delta T, which is 41. You should get a value for Q of 25,707. And remember, Q here is in joules. Okay, we still haven't worked out the enthalpy change because Q is the energy change. Okay, if you remember, enthalpy change, so in this case it's enthalpy change of combustion. This is given to us by doing, so if you remember the units for this are kilojoules per mole. Okay, at the moment we've got something in joules, so we need to convert that into kilojoules first. So I'm going to do my Q in kilojoules divided by the mole. So this is where we're going to use the fuel because we're going to calculate the moles of the fuel burnt. Okay, so let's just quickly convert our Q into kilojoules. All I need to do is divide this. Remember, to go from joules to kilojoules, we divide by 1,000. So I'm just going to divide this number by 1,000. So to get my Q in kilojoules, I'm going to do my joules divided by 1,000. and that's going to give me 25.707 kilojoules. Okay, so now I've got my Q in kilojoules. I just need to work out the moles of the fuel burnt. So I'm just going to move down here. So the mass of my fuel is 1.6. Now if I want to work out moles from mass, it is mass in grams divided by the MR. Okay, my mass here is 1.6 grams. My MR, so methanol, is CH3OH. I've already worked out the molar mass, so that is 32. If I do that, I get 0.05 moles. Okay, so I've now worked out my moles of fuel burnt. So now if I go back to this equation here, my Q in kilojoules was 25.707 kilojoules. If I now divide that by my moles, which is 0.05, that's a 5. This answer is now going to be 514.14, and my units for this are kilojoules per mole. Okay, so this over here is the answer I get through my calculation. Okay, but this here is not my final answer. Okay, I haven't decided what the sign should be. Now this is not something you're going to get through the calculation. This is what you're going to get by looking at the temperature change. Okay, if we look over here, during the experiment the temperature increased. We went from 21.5 to 62.5. That was a temperature increase, so that tells you it's an exothermic reaction. Okay, and as we know, the delta H for an exothermic reaction should be negative, so we have to now decide that sign. Okay, as we know, combustion reactions are always going to be negative, so that should be fairly straightforward. But just by looking at the temperature change, we can see it was a hot reaction and therefore exothermic. And so our final answer is actually minus 514.14 kilojoules per mole. Okay, and it's very important that you put that sign in because you lose a mark if you don't put that negative sign in. So our final answer for the standard enthalpy change of combustion of methanol is minus 514.14 kilojoules per mole. Okay, let's now have a look at how accurate this experiment is. Because obviously it's an experiment, there may be lots of reasons why that value that we get is not the same as the one in the data book. Okay, obviously the data book one is considered more accurate, so there may be reasons why it's not that exact value. And there are actually 4 reasons why, and you need to know these 4 reasons really well. So I'm going to talk through each of them. The first one is due to a major error in this experiment. In this experiment, not all of the heat in this setup over here is going to the water. Okay, as we can see, a lot of the heat can escape to the surroundings. So a major source of error in this experiment is the heat loss to the surroundings. Okay, in this experiment, because we are using a liquid fuel, when liquid fuels get hot, they can evaporate quite easily. Okay, any fuel that's left in the wick after we extinguish the flame, that can evaporate and therefore take away some of the mass. And essentially, if the fuel evaporates, when we take our mass, it's going to be less than expected. Okay, so that fuel that's evaporated hasn't been burnt, and therefore when we include the mass of that, it's actually giving us a more inaccurate value of the mass of fuel being burnt. Okay, so with these fuels, they can evaporate, and that can lead to our experimental value being inaccurate. Another thing that can lead to inaccuracies is the fact that we are assuming that complete combustion is occurring. Okay, that's an assumption we're making, but the truth is we don't know that. It could be that some incomplete combustion is occurring. Okay, and as we know, incomplete combustion actually uses more energy, and therefore that can make our final enthalpy change value to be inaccurate. Okay, Another thing is, if we're doing this in a lab, it could be that we don't actually have standard conditions in the lab. Okay, we might not be at 298 Kelvin. We might not be at 100 kilopascals. So that could be another source of error in this experiment. Okay, when you're doing, or if you're asked in an exam question, you know, what are the sources of error, or why is that value not accurate, you've got to make it specific to the experiment. Okay, and these 4 points here are specific to standard enthalpy change of combustion, and therefore you need to remember these 4.